This learning module that we're in now, number 3, and the next one, number 4, introduce what is one of the most important concepts of this class. And that is this idea of something called the time value of money. Compound interest, discounting interest, the time value of money. Now, before we jump into doing calculations and working with Excel and all that sort of thing, I want to make you all an offer, right? A thought experiment, not a real offer, but make you an imaginary offer. And here's the offer. I can either give you $100 now, right now, $100 in your hand, or I can promise that a year from now, I will give you that $100. Right? So there's the offer. Either $100 right now in your hand, or the promise, sincere promise, a year from now of $100. Which do you prefer? Now, of course, this experiment works a little better if we're all together in the classroom and we can talk back and forth, but still, which would you prefer? Now, I know from experience that pretty much everybody says, well, I want the $100 in my hand right now. Not surprisingly. But then the question becomes, why? Why is it that you prefer the $100 now rather than waiting a year for me to give you that $100 bill? And I promise that I will give you the 100 a year from now. Why is it that you prefer the 100 now? Well, basically the answers I get boil down to 3. 3 reasons why people prefer the 100 now. Pardon me. The first one is interest. If I gave you the 100 now, you can invest it, and a year from now, you will have more than 100. How much more? Well, that depends on the interest rate and something called compounding that we'll talk about in a bit. But there's one reason. Because of the interest. If I give you 100 now, you can invest it, and a year from now, you'll have 100 plus the interest it's earned, more than 100. All right, so there's one reason why to prefer the 100 now. Another reason why to prefer the 100 now is inflation. What does inflation have to do with anything? Well, first of all, what is inflation? Well, if you think back to your macro econ days, inflation is a measure of the increase, or it could be decrease, but increase in the general level of prices. And hopefully you remember the discussion of the consumer price index and a basket of goods and services with their prices measured at a certain point in time and then compared to that same basket at some point in the past. Hopefully that seems familiar. I should have checked. Inflation is not terribly high right now. What is inflation? 4%? That might be too high. What does that mean? What does that mean, 4%? Well, what that basically means is that the general level of prices is increasing at about 4% a year. Now, does that mean the price of every single thing is rising by 4%? No. No, because we're not measuring it by every single thing. But it means that in general, prices are rising at about 4%. Some prices might actually be falling. So what does that have to do with our $100? Well, If I give you $100 today and you hold on to it, prices over the course of a year will be going up, won't they? And at the end of the year, your $100 will purchase less than it could today. Right. In other words, if I give you the 100 today, you can go out and buy X amount of goods. But if you wait a year for me to give you the 100, prices will have gone up in the meantime, and that same 100 will buy less goods. So in a sense, the value of your 100 decreases. The purchasing power of that 100 will decrease just because of inflation and rising prices. Right? So if you're going to spend it, you're better off to get it now so you can spend it when prices haven't risen by however much. All right. One reason to get 100 today, because if I get it today, I can invest it and I'll end up with more than 100. Second reason, I want the 100 today because if I wait, inflation will erode the purchasing power of my 100. And the third one, the third reason that comes up is risk. The risk that even though I have promised faithfully, cross my heart and hope to die, stick 1,000 pins in my eye, I promise that I will give you that 100 a year from now. There's still a risk that I won't. That even though I intend to, something might happen and I'm not able to. So that having it in my hand means I've got it and I don't have to wait and wonder whether or not you'll get the 100 a year from now. Right? At this point, it's kind of worth talking just a little bit about this concept of risk in finance. And really, risk is the basic concept in finance. Risk is the possibility, and I don't want to say probability because that opens a whole can of worms, but the possibility that what you expect and what you actually get are different. All right, let me say that again. Risk is the possibility that what you're expecting to get and what you actually get are different. And we'll talk a lot about risk over the course of this semester, about what it is and how it works and how we can measure it and what it's worth, all those kinds of concepts. But for now, it's enough to say that I want the $100 bill now because there is a risk that I won't get it a year from now. All right? Even though I expect to get it, it may not work out that way. Risk. So why would you prefer the 100 today? Well, 3 reasons. Interest, inflation, risk. Now let me turn the offer around. Let me turn it the other way. What if I offered you $100 today, or at the end of the year, I will give you $100 plus the interest you have earned, plus enough to make up for inflation, plus a premium for risk. Those are the 3 things that kept you wanting the 100 now. Right? So instead, let's change it. 100 today, or 100 plus interest, plus inflation, plus an amount to cover risk. Now, which do you prefer? Well, I know that everybody still probably wants the 100 right now. I get it. But at least now it's something to think about, right? I mean, before it was obvious. Why would I wait a year to get the same amount of money? But now if I wait a year, I'm going to get, the 100 plus interest plus inflation plus risk. Well, the fact that we can even think about that possibility, right? The fact that that makes you even stop and think makes my point. My point is that money, let me say it differently, time, that year, has value. Waiting a year changed things. 100 now or more than 100 a year from now. And the question, of course, becomes how much more? Right? How much more? Well, we're not going to really get into that at this point, but I want to introduce a really, really important concept, one that we'll use all the time. And that is the concept of an investor's required rate of return. Right? And what from in this discussion, that required rate of return is the interest and inflation and risk. Right? I'll either take the 100 now, or I'll take the 100 a year from now plus my required rate of return. All right. And that required rate of return, it depends at least on interest, inflation, and risk. So, so we can see that the passage of time has value, hence the name time value of money. The amount of value that time has depends upon an individual investor's required rate of return, interest, inflation, risk. So the new thing, that the tool, if you will, that I'm going to introduce here is how do we turn the $100 today into that future amount? Pardon me. How do I take that 100 today and increase it by the required rate of return to get the future amount? And as we'll see, we can even do that backward. We can say, if this is the amount in the future, can I decrease it by the required rate of return to see what that would be today? Right? That's what I mean by the time value of money. And you can see that that required rate of return is basic to the whole idea of the time value of money, and either increasing money into the future or decreasing it back to the present. Okay. As I said, we will use required rate of return all semester, right? Basically, from here on out, we'll be dealing with the required rate of return. But at this point, since we're just introducing it and learning how to use it, let's leave aside risk, and let's leave aside the inflation and just concentrate on interest. For now, let's just assume that our required rate of return is only the interest rate. All right, we'll leave inflation and risk aside. Believe me, we'll be back, particularly for risk. We'll be back and bring them back into the picture. But for now, let's just concentrate on interest. Right? So taking an amount today and increasing it into the future simply means increasing it by the amount of interest that it would earn. And the other direction, taking an amount in the future and decreasing it back to the present, means taking away the interest that it would earn. We can go either direction. It's the same thing, just turned backwards. Right? But for now, let's only think about interest. Believe me, we'll get risk back into the picture later. All right, one other concept before we jump into this is the idea of compounding and compound interest. Basically, compound interest means that the money you invest, earns interest for a certain amount of time. And at the end of that amount of time, all the interest you've earned also begins to earn interest. All right, let me say that again. If we invest our $100, we'll earn interest for a certain amount of time. And at that point, the 100 and the interest we've earned all begin to earn interest moving forward. Okay? Compound interest, compounding. Depending on what you're investing in, depending on the situation, compounding might be once a year, which means our $100 would earn interest for the entire year, at which point the 100 and the interest begin to earn interest for the second year, and so on and so on. Or we could compound semi-annually, meaning twice a year or every 6 months. All right, invest your 100, it earns interest for 6 months. At that point, the 100 and the interest you've earned both begin to earn interest for the next 6 months, and so on. Right? We could earn interest quarterly, or we could compound quarterly. Every 3 months, that interest begins to earn interest. We can compound monthly. All right, we see that a lot. Right? Your loans with monthly payments are basically compounding monthly. Right? They earn interest a month, per month. We could compound daily. We could even compound continuously, so that the compounding period is basically infinitely small. It's always compounding. I don't think we'll jump into that quite yet, but so if I invest my money, if I invest this 100, that's the possibility, how much will I earn? What is if that's the present value, 100, what will the future value be? The 100 plus all the interest we've accumulated. Well, we can see now that that depends on about 3 things, right? It depends on the interest rate. It depends on the length of time. And it also depends on the compounding. Right? Everything else being equal, same 100, same interest rate, the more frequently we compound, the more money you'll end up with, because that interest earns interest more often. It's almost like a snowball rolling down the hill, right? The faster it rolls, the bigger it gets. Right? And taking it the other direction, if we're looking at an amount in the future and we're looking to take away interest to get it back to the beginning, everything else being equal, the more often we compound, the smaller that present value will be. All right, so what we're interested in right now is how to do that calculation, how to take an amount today and turn it into an amount in the future, or vice versa. Now, back in the day, I used to ask students to buy a financial calculator. Texas Instruments BA2 Plus financial calculator cost about $40, $45. And we would use that to do these calculations. Very simple, very straightforward. And as time passed, I came to the realization that all students who are not finance majors are unlikely to use that calculator again. And I'm asking you to spend $40, $45 just for something that's just going to go and sit in the drawer. So instead, what I want to do now, instead of using a calculator, I want to use a tool that I think you are more likely to use in the future, and that's Excel. So that we're going to learn how to do this time value of money, compounding, discounting, these calculations. We're going to learn to use it in Excel rather than on a calculator. All right. Okay, as always, I've given you a handout with this idea, this concept, this lecture in the handout, and also some examples. Right. So let me go ahead and share that now, and we can get into our discussion of the time value of money. Okay, so those of you who are familiar with Excel, and I hope most of, if not all of you are, the idea of Excel is always we type formulas into cells and it does the calculation for us. We tell Excel what we want to calculate and how, put it in the cell, and it does the calculation and shows us the answer. Okay. For the time value of money in Excel, what Excel wants us to tell us is what's the function and what are its arguments, right? And it's always in the form of the function, this f, followed by parentheses, and inside the in parentheses are all the arguments. Now, a minute ago, I said, if I'm taking an amount today and turning it into an amount in the future, the future amount is determined by the interest rate, the compounding, and the length of time. And those are the things that go in here in the parentheses. Those are the arguments that we're talking about. If I'm taking an amount today and compounding it, increasing it into the future, in that case, the function is future value, FV. And inside the parentheses are the amount today, the interest rate, the compounding, and the length of time. Put that into Excel, it reads us the answer. All right. Or, as I said, we can go the other direction. We can start with an amount in the future and take away the interest, discount the interest. In that case, the function would be present value, PV. And inside the parentheses would be the arguments. What's the amount in the future? What's the interest rate? What's the compounding? What's the length of time? And it will give us the answer. All right. And it's really very simple. The trick is that the arguments always have to be in a certain order. That's how Excel knows what you're telling it. The arguments must always be in the same order. And here it is. Here's the order. All right. First has to be the interest rate, then the number of periods, payment amount. Let's not worry about that for the moment. Present value or future value, and type. Again, let's not worry about that for the moment. Right? So what happens is we basically pull one of these arguments out and make it the function, and then fill in the rest of them and get the answer. Okay. Now, the one thing that I want to make sure of, make a special point of before we do any examples, is that the rate argument is the interest rate per compounding period, which might be per year, but more often not. When I say per period, I mean compounding period. If we're compounding annually, 1 period per year. If we're compounding semi-annually, 2 periods. Quarterly, 4. Monthly, 12. All right. So it's not the interest rate for the entire year. but only the interest rate for one compounding period. Right? If the interest rate were 10% a year and we're compounding semi-annually, twice a year, the rate per period would be 5%. If it were 10% a year and we're compounding quarterly, 10 divided by 4, 2.5%. It's not the rate per period, not the rate per year, but the rate per compounding period. All right. Same thing with NPER, number of periods. It's not the number of years, but the number of compounding periods. If we invest for 5 years, compounding annually, that's once a year for 5 years, 5 compounding periods. But if we invest for 5 years compounded semi-annually, that's twice a year for 5 years or 10 compounding periods. Right? Monthly, we're investing monthly for 5 years. That's 12 times a year for 5 years or 60 compounding periods. Okay? Very important to keep in mind. The rate that goes in here in the arguments is the rate per compounding period. And the number of periods is not the number of years, it's the number of compounding periods. All right? We just use the ones we need. If we don't need it, we have to put a 0 in there to hold its place, because Excel wants things in exactly this order. But the last two, they're in brackets. If we don't need them, we can just leave them out. All right, a lot of talk. Let's see how this works. Right. Number 1, calculating future values. What does that mean? Well, that means I'm taking an amount of money today and compounding it into the future. I'm taking that money and increasing it by the amount of interest. And the amount of the increase is going to depend on the length of time, the interest rate, and the compounding. So let's look at this first example. I have $3,150 today in the present. That's the present value. We're investing it at 13% a year for 7 years, compounded annually. All right. Remember that the rate I need for my calculation is the rate per compounding period. In this case, the compounding period is 1 year, and the rate is per year, 13% per year, so I leave it alone. My rate per 1 year compounding period is 13. And I need the number of compounding periods, the total number of compounding periods. Well, annual compounding for 7 years. That's 1 time a year for 7 years, 7 compounding periods. Right? And here just below, here is the Excel calculation. Now, just above it, I've done it algebraically if you're interested, right? But we're just going to stick with Excel. All right, so I'm taking an amount today and turning it into an amount in the future. That means my function is FV, future value. And here are my arguments. All right, if you look, I can't get them both on the same screen. If you look at the order, the first argument is the rate. The rate per compounding period. In this case, because of annual compounding, that's 13%, 0.13, 13%. All right, Excel deals in decimals. The second argument is number of periods, NPER. Well, remember we said once a year for 7 years, 7 compounding periods. The next argument is payment, PMT. We're not dealing with that right now, but we have to put a 0 there as a placeholder so the Excel knows the order. The next one is present value, right? And I said I had 3,150 today. 3,150, make it a minus sign, and I'll come back in a minute and tell you why. You type all of that equals future value, parentheses, 0.13, comma, 7, comma, 0, comma, minus 3150, comma, hit enter, and Excel will tell you 7,410.71. What is that 7,410.71? Well, that's the 3,150 we started with, plus 7 years worth of interest at 13% compounded annually. We end up with 7,410.71. All right, a couple things. Why the minus sign? Well, the minus sign is because of the algorithm that Excel uses. And in this Excel, if you put in a negative number, it will give you back a positive number. And that's what you see. I put in a negative 3,150. I got out a positive 7,410.71. If, on the other hand, I had put in a positive 3,150, the answer would be minus 7,410.71. That's the algorithm with Excel. And if you put in a negative number, it gives you a positive. If you put in a positive number, it gives you a negative number. So just for the sake of being consistent, let's make our present values negative numbers so it gives us an answer, a positive number. All right? It's just the algorithm. It's just a quirk in Excel. What would happen if you just put in 3150? You'd get a negative answer. And at this point, it doesn't matter. Negative and positive will matter as we move on. But for now, it just kind of confuses things. So I like to make the present values negative so that I get a positive answer. All right. The other point, the other thing that I want to make, and it's important. I've lost my cursor. There it is. The other thing is important is future value. What we calculated is always greater than present value. Always. Future value, FV, is always greater than present value. Why? Well, because future value is the amount we started with plus all of that compound interest. Right? We start with the present value, we compound the interest, and we end up with the future value, and the future value will always be greater. Unless the interest rate we're using is 0 or negative, but we're not going to use either of those. So in our world for this class, future value is always greater than present value. If you do a calculation and you find out the future value answer you get is less than what you started with, you've made a mistake. Future value is always greater than present value. All right. As you can see, I've given you 4 examples. I don't know that it's necessary to go through all 4, but let's just do the second one. Right? if I have 8,453 today, I invested at 7% a year, compounded annually for 16 years, how much will I end up with? In other words, if I take a present value and amount today and I compound interest onto it, how much will I end up with? Well, here's the calculation. We're finding the future value. We start with present value, we compound to get the future value. Right? Equals future value, there's the function. In the parentheses, always in the same order. First is the interest rate, right? We said that was 7% a year, 0.07. Number of periods, 16, once a year for 16 years, 16. 0, that's payment, PMT. We're not worried about that at this moment, but we have to put the 0 there as a placeholder. And then the present value, 8,453, and I made it negative just because of that quirk in the algorithm. And I get 24,954.64, right? Equals FV parentheses. Put in all the arguments, close parentheses, hit enter, and you've got the answer. Now, a question we're going to be asking ourselves a lot is this a reasonable answer? And by that, I mean, is the future value greater than the present value? In this case, yes. Had I come out with an answer smaller than the 84.53 we started with, that would not be a reasonable answer. All right. In this case, it's reasonable. Right? Since we're using Excel, it's possible if you make a mistake in what you're entering, you'll get the wrong answer. And one way to pick that up is ask yourself, is this reasonable? Could this be the answer? Okay, well, moving on. All of those examples were using annual compound. What would happen if I changed it to semi-annual compounding? What would happen here to this first example if instead of annual compounding, I changed that to semi-annual compounding? Well, semi-annual compounding means twice a year, doesn't it? All right, so that would mean that we earn that 13% for 6 months, and at that point, it begins to earn interest on itself, compounding twice a year. All right, now remember that our calculation doesn't want necessarily the rate per year, it wants the rate per compounding period. And at semi-annual, the compounding period is half a year. So I have to divide the interest rate by 2. 13 is for the entire year. I need the interest rate for a half a year. Half of 13 is 6.5. At the same time, the number of periods is not years, but rather number of compounding periods. And now we have twice a year for 7 years, or 14 compounding periods. And here's our calculation. Excuse me. The function is equals future value, and now instead of 13%, it's 6.5%. The number of periods is not 7 anymore, it's 14. Still a 0 for that payment placeholder, 31.50. Future value we get 7,606.85. Is that a reasonable answer? Yes. It's more than we started with. It's more than the 3150 we started with. Yes, it's a reasonable answer. Right? So that when we changed compounding, we changed both the rate and the number of periods. And that will always be true. If you change compounding, that's going to affect the interest rate and it's going to affect the number of periods. Both change every time you change the compounding. All right. In this case, we divided the interest rate by 2 for semi-annual, and we multiplied the number of periods by 2 for semi-annual. Had it been quarterly, we would have divided and multiplied by 4. Monthly, divided and multiplied by 12. The point to remember is that we have to adjust both the rate and the number of periods. The other thing to notice is that more compounding increases the future value. When we did annual compounding, our future value was 74, 10, 71, wasn't it? When we increase the compounding, our future value gets bigger. More compounding increases the future value. If we changed again and compounded quarterly, pardon me, we'd divide the 13% by 4. And we'd multiply the 7 by 4. And we would end up with a still larger future value. All right. So future value is always bigger than present value, unless the interest rate is 0 or negative, but we're not going to deal with those. And the more often you compound, the bigger the future value. All right. And again, here are all the other 3 examples worked out for semi-annual compounding. All right. So you've got 4 examples taking an amount today, turning it into an amount in the future with annual compounding and semi-annual compounding. In each case, I've worked it out algebraically and in Excel. I'm only going to expect you to be able to do the Excel. Okay, so number 2, let's go the other direction. Right? Our first example, I took an amount today and I compounded the interest on top of it to see what we could end up with. Now let's go the other direction. Take an amount in the future and discount or take away the interest to see what that would be worth today. I take an amount in the future, discount the interest to make it today. Right? Why would you do that? What a weird thing to do. Well, imagine that you needed $100 in the future. This would allow you to decide how much I had to invest today to get to that 100 in the future. Depending on the length of time, the interest rate, and the compounding. Right? We call it discounting or present value. Take an amount in the future, discount it today. In other words, take the compound interest away to see what it would be worth today. And once you've done that, now you know what you have to invest today to end up with that amount in the future. So again, here are 4 examples. Right? We'll start with annual compounding. We'll just start with the first one. Why not? Imagine that I need 17,328 in the future. right? How far in the future? 15 years in the future. If I can invest at 7% compounded annually, how much is that worth today? In other words, what is the present value of 17,328? Well, in Excel, the idea is exactly the same. Only in this case, we take out the PV and make it the function equals PV. That tells Excel what you want to find. And then we have to tell it all the inputs. First is always the rate, 7%. Then the number of periods, 15 years, and it's annual compounding, so I don't have to divide or multiply or any of that. Next is payment. We're not using it, but we've got to put that 0 as a placeholder. Right? The next in the list is PV, isn't it? But we've already pulled out the PV and made it the function. So we put in future value, 17,328. So our list of arguments is rate, number of periods, payment, PV got pulled out and made the function, and future value. Right? There's also type, but that's in the brackets, so we can leave it out if we need to. We don't have to put a 0 in to hold its place. All right, put all of that in, and I get 6,280.46. Where did the negative sign come from? Remember that quirk in the algorithm, that quirk in Excel. If you put in a positive number, 17,328, you get a negative number, right? In this case, the present value is negative. It's not really a negative number. That's just Excel. All right, but that's me kind of trying to be consistent so that our present values are always the ones that end up being negative. At this point, you can ignore the negative sign. Right. It'll be important later, but for now, that's just the algorithm. That's just that quirk in Excel. Okay, so what do we know? Well, we know that if we invest 6,280.46 and we invest it at 7% for 15 years, compounded annually, we will end up with $17,328. In other words, I took the 17,328 and discounted away the interest to see what it's worth today. 6280.46 is the present value. 17,328 is the future value. Is it a reasonable answer? Well, present value is always less than future value, unless we're using an interest rate of 0 or a negative rate, which we're not. Present value is always less. Pardon me, ignore the negative sign. 6280.46 is less than 17,328. If I invested 6280.46 at 7% for 15 years compounded annually, I would get 17,328. Right, the next one, same idea. Right, here's the calculation. Equals PV is the function. Whoops, I rolled too low. Our rate is 11%. Our number of periods is 8. Since it's annual compounding, we don't have to divide or multiply or any of that stuff. 0 is the placeholder for payment. We pulled out PV to be the function. 41,517 is the future value. Close the parentheses, hit enter, 18,015.33. Is that a reasonable answer? Well, 18,000 is less than 41,000, so yes, it's a reasonable answer. Now, of course, I can't just leave it alone there. We have to look at different compounding. So let's do the same calculation now for quarterly compounding. Quarterly compounding, which means every 3 months or every quarter, the interest we've earned begins to earn interest itself. Right? And that means by changing the compounding, we're going to have to divide the rate by 4, and we're going to have to multiply the number of years by 4. I don't want rates per year. I want rates per compounding period. Now, in the first example, the compounding period was a year, so we didn't have to mess with it. But now the compounding period is 1/4 of a year. So I have to divide the rate by 4, and I have to multiply the number of periods by 4. Right? Rates are divided by 4, periods quadruple. Right? In the first example, in that first example we did just a second ago, the rate was 7%. Now I divide 7% by 4 and I get 1.75%, 0.0175. The number of years was 15, but 4 times a year for 15 years is 60. 0 to hold the place for that payment. Present value becomes the function. 17,328 is the future value. 6,119.04 is the present value. Is it a reasonable number? Yes. Present value is smaller than future value, ignoring the negative sign. The other thing to point out at this point is that more compounding means smaller, present value. Right, annual compounding, our present value was 62.8046. Quarterly compounding, our present value is only 61.1904. The more frequent compounding means we discounted away more interest. So the present value gets smaller. All right, really important rules to remember. Present value is always less than future value. Future value is always greater than present value. More frequent compounding makes future value bigger, but more frequent compounding makes present value smaller. Okay, in the second example, our rate was 11 and our years were 8. We change it to quarterly. I divide 11 by 4 and get 2.75. And I multiply 8 by 4 and I get 32. All right. So important. When we change the compounding, you have to adjust both the interest rate, divide it, and the number of periods, multiply. Both have to change. Okay, so thus far we've taken this concept of a required rate of return, excuse me, pared it down just to interest rate. We'll add back the risk later. And now we see how we can take an amount today and see how much it will grow to given interest rate, compounding, and amount of time, future value. We can also take it backward, an amount in the future, discount it back to today using the same three things: amount of time, interest rate, and compounding. Right? We can also kind of look inside those calculations and ask ourselves, pardon me, if we have an amount today and an amount in the future, what must the interest rate be? I mean, if I need to get from A to B, what interest is it going to take? Or we can ask, if I have A and B and the interest rate, how long is it going to take me there? In other words, our inputs are present value, future value, rate, and number of periods. And if we know any three of those, we can calculate the fourth. In the first example, we knew rate, periods, and present value, and we found future. In the second group, we knew future, rate, number of periods, and we found present. Now, if we know present and future and number of periods, we can find the rate. Or if we know present and future and the rate, we can find the number of periods. Any three, you can find the fourth. Okay, so I'm going to share that handout with you again, and we'll see how that works. All right, continuing down. Right now, instead of future value or present value, let's calculate the rate. Right, and let's just jump into an example. Right. If I know I have 715 today, and I need 1381 at the end of 11 years, what interest rate must I earn? And in this example, our compounding is annual. Let me say that again. I know the amount today, and I know the amount I need in the future. I'm going to invest for 11 years at annual compounding. What rate must I earn? Well, the idea is the same. Right? We go to Excel, we pull out rate, make it the function, equals rate. Right? So rate is gone, and the next one is number of periods, isn't it? 11. 0 is the holder for the payment. Present value is 715, and let's make it negative. Remember that quirk in Excel. Make the present value negative. The future value, 1381, close parentheses, and you get 6.17 per year. Excuse me, what does that mean? Sorry, I can't live without Topo Chico these days. What does that 6.17% mean? Well, it means if I take my 715, invest it for 11 years at 6.17%, I'll end up with 13.81. All right, given the present and the future and the amount of time, what rate? 6.17%. All right, now before we move on, just a second about this negative positive. You have to have both a negative and a positive, or Excel gives you an error message. And I think it says error 5, but I couldn't swear to it. Right? You must have both negative and a positive, or you'll get an error message. And like I said, I think it says error 5. Right? So here's an example. If you know any three, you can find the fourth. We know present value and future value and number of periods. So we can find the interest rate. But what happens if we change the compounding? not annual, but semi-annual. Well, let's see. We have to adjust both the rate and the number of periods, don't we, when we change compounding? All right, so let's see how that would work out, changing from once a year to twice a year. We pull out rate to be the function so that the first item is the number of periods, and I took that 11 years, multiplied it by 2 to get 22 compounding periods. Twice a year for 11 years, 22. 0 is the placeholder. 715 is present value. 1381 is future value. You got to make one of them negative. Right? It could be either one. I like to be consistent and always make present value negative. Close the parentheses, hit enter, and I get 3.04. But that is 3.04 per semi-annual period. Right? How do I know that? Well, because our number of periods was 22, and that's semi-annual. So Excel gives us a semi-annual rate. I don't want semi-annual. That doesn't make sense. Nobody talks about that. We want it annual. All right, so how do I turn 3.04 semi-annual into annual? Well, let's multiply by 2. 3.04 semi-annual times 2 gives me 6.08 per year. Right? When we're doing this calculation for rates, never leave it per compounding period. Always adjust it for annual. All right, if the compounding is semi-annual, that means multiplying by 2. If it's quarterly, that means multiplying by 4, and so on. All right, that wasn't an issue for the dollar amounts, was it? For the present value, future value. And now it is. Our interest rate needs to be, our final answer needs to be in annual terms. All right, now notice that annually required us to earn 6.17. Semi-annually, we only have to earn 6.08 a year. Why? Well, because that compounding lets the interest accumulate more. We're earning interest on top of interest on top of interest. So, pardon me, we can earn a lower interest rate and still get where we need to be. If we change from semi-annual to quarterly, right, then our answer would be still a little smaller because it's interest piled on interest again and again and again. Okay? All right, the second example, right? The second example here, 905 was the present value, make it negative. Excuse me. 1718 is future value. 8 years annual, so it's 8. We're the placeholder there for payment. 8.34%. And we don't have to multiply by anything because our compounding is annual. If we go semi-annual, then it's not 8 years anymore, it's 16 periods. Our answer is 4.09, but that's semi-annual, so I got to multiply by 2, and I get 8.18 per year, which is slightly smaller than what we got with annual compounding. Right? And that's because the more compounding, the more the interest piles on the interest, and it gets us there faster, if you will. All right, one thing more. One thing more, and that's calculating the number of periods. I think you can probably anticipate how this is going to work. We know any 3, we can calculate the 4th. All right, so let's assume that we have 195 today, present value. We need 875 in the future, and we can earn 9% a year compounded annually. How long will it take? Well, that's easily done in Excel. Now the function is number of periods, NPER. Excuse me. We pull NPER out and make it the function. The first item is rate, 0.099%. Right? The next one should be number of periods, what we pulled it out. So it's payment, and there's that 0 placeholder for payment. Minus 195 present value, and make it negative or you'll get an error message. 875 future value, close the parentheses, hit enter, and it says 1742, and those are years. How do you know that those are years? Well, because our compounding is annual. Right? Our number of periods is number of years because our compounding is annual. All right, so what do we know? Well, if I have 195, I invested at 9% a year, compounded annually, it'll take me almost 17 and a half years to get up to my 875. Right? Now, if I change that, because I can't just leave it alone. If I change that same calculation to quarterly, right, now it looks the same, right, except I took my 9% and now I divided it by 4 for the quarterly compounding, and there's where I get 2.25%. 9 divided by 4 is 2.25. Right, 2.25%. NPER we pulled out to be the function. 0 is the payment. Present value, future value. I get 67.47, but these are not years. Those are not 67 years. Those are 67 quarters. How do you know that? Well, because we're using quarterly compounding, and the period is quarterly. This is 67.47 quarters. Well, I don't care how many quarters it takes. I want to know how many years. So I take that 67 and divide it by 4, and I get almost 17 years, 16.87 years. Right? Why didn't I have to make that adjustment before? Because we were compounding annually and my answer was already in years. Here, my answer is in quarters, and I need to change it to years. So I divide by 4 to get 16.87 years. Oops, wrong line. Okay. When we were talking about interest rates, calculating the interest rates, I said, don't leave it per period, change it to be years. Same thing here. Don't leave it in number of periods, change it to be years. What you'll notice, I hope, is that it took us 17.42 years with annual compounding, but only 16.87 years with quarterly compounding. Well, that's again because the more frequent compounding means interest is piling on interest is piling on interest, and we get to our goal faster. Okay? Right. Okay. I think That's enough for now. So what we've done is we've started with this idea of me making you an offer, 100 today or 100 a year from now. No. But how about 100 today or 100 plus your required rate of return a year from now? Well, now we can think about it. Right? And we said that required rate of return is probably going to include interest, inflation, and risk. Let's leave aside everything but the interest. And now we've seen how Excel can help us take an amount today and compound it into the future. Present value becomes future value. Or take a future amount and discount it back to today. Or if we know any of the three, present value, future value, rate per period, number of periods, if we know any three, we can always find the fourth. All right, important to ask ourselves, is it a reasonable answer? Present value is bigger than future value. Or excuse me, present value is smaller than future value. Future value is greater than present value. The more often you compound, the bigger the future value. The more often you compound, the smaller the present value. Okay, if you have questions, be sure and email me. I'll do my best to get back to you. Thanks.